Welcome to this explainer. Okay, today we're popping the hood on modern generative AI to look at something pretty incredible. Every single time you ask ChatGPT a question or do a reverse image search, you're actually kicking off a monumental behind-the-scenes challenge, organizing and searching massive vector databases. And that is exactly where the Faiss Library steps in. We're going to demystify how this amazingly powerful tool organizes massive amounts of data so efficiently that what seems frankly mathematically impossible just happens in the blink of an eye.
Okay, let's dive into this. How do AI systems search a billion data points in milliseconds? Seriously, imagine having to flip through every single book in the world's largest library just to find one specific quote. Finding similar AI embeddings at scale is a massive computational bottleneck. Without highly specialized infrastructure, fetching a single result could literally take days of raw processing power. Yet, today's applications do it instantly.
Now, don't worry, we're going to break this complex topic down into a structured, really easy-to-follow map. 1. The vector search problem. 2. Measuring distance with Faiss. 3. The speed versus accuracy trade-off. 4. Shrinking data with quantization. And finally, 5. Smart search refining results. All right, part 1. The vector search problem. Basically, the impossible problem of brute forcing billions of high-dimensional vectors.
To really understand the problem, we first need to get a handle on how modern AI sees the world. It uses what we call embeddings. Embeddings are simply vector representations, just lists of numbers churned out by neural networks. You can think of them like GPS coordinates for meaning. They map media, whether it's a block of text, an image, or an audio clip, into this complex mathematical space. And the key thing to remember here is that in this space, distance directly reflects similarity. If two text embeddings are sitting close together, their underlying meaning is highly similar. So finding the nearest neighbor to your query gives you the most relevant content.
So the million-dollar question, how do we actually find that nearest neighbor? Well, brute force search gives you perfectly exact results because it exhaustively checks every single vector in the database. But at scale, it's computationally paralyzing. It's just way too slow. The clever, highly optimized solution to this is approximate nearest neighbors search, or ANNS. With ANS, you accept slightly imperfect results in exchange for lightning-fast speed. Instead of checking everything, the algorithm just cleverly searches specific, relevant neighborhoods of data.
Moving right along to part 2, measuring distance with Faiss. This is our baseline solution, looking at how Faiss fundamentally calculates the similarity between these vectors.
And this brilliantly illustrates how different metrics actually measure that similarity. Faiss gives developers a full toolkit. You've got the classic L2 Euclidean distance, basically a straight-line geometric measurement. There's inner product, which is a heavy lifter in recommendation systems like Netflix or Spotify. Cosine similarity measures the angle between vectors, treating them like arrows pointing out from a center origin. And then there's Mahalanobis, which actually calculates distance in a transformed space based on how your data is distributed.
But guys, here is the incredibly brilliant part. Instead of building totally separate, bulky search architectures for every single one of those metrics, developers mathematically trick the system. They map one metric to another to save computation time. You can map cosine to inner product simply by normalizing your vectors beforehand. You can even map inner product to L2 just by adding one single extra dimension to the vector. So under the hood, Faiss is running these blazingly optimized L2 or inner product searches no matter what metric was originally asked for. It's genius.
Section 3. The speed versus accuracy trade-off. In the world of ANS, developers have a strict computational budget, forcing a compromise between time, accuracy, and memory.
This budget means we are constantly hunting for what's called the Pareto optimal frontier. That's a fancy way of saying we want the absolute fastest speed possible for a specific accuracy level, or the highest accuracy we can squeeze out of a strict time budget. Now, Faiss index structures have a ton of search time hyperparameters, and testing every single combination would literally take lifetimes. But Faiss manages this hyperparameter space for you, pruning out the bad setups to lock you into that optimal sweet spot without you having to exhaustively test everything.
All right, part 4, shrinking data with quantization. We're moving into the optimization phase now. And you can really treat this vector compression like a brilliant heist movie workaround. If the payload is too heavy to carry, you just shrink it down.
Which brings us right to quantization. Simply defined, quantization is a compression method. It takes a continuous multidimensional floating point vector and converts it into a tiny, highly compact integer code. Instead of hoarding these massive strings of decimals, you're storing a simplified code, which drastically saves memory. This is what allows those vast, sprawling datasets to fit right into fast RAM instead of dragging along on slow disk storage.
Faiss breaks this down using a few different codec strategies. First, the k-means quantizer, which maps vectors to learned checkpoints and is highly accurate. Then you have scalar quantizers, which just chop each dimension independently into tiny 8-bit or even 4-bit chunks for pure simplicity. And finally, multi-codebook quantizers. These combine several smaller compressions together, striking this fantastic balance between keeping the code size tiny while keeping accuracy high.
Now, what's really interesting about this is that specific number, 16 million. See, while that k-means quantizer is super accurate, it actually hits a hard mathematical ceiling at about 3-byte codes, which equals 16 million centroids. If you try to push past that, the memory usage and the complexity of encoding just grow exponentially. It completely breaks down. That limitation is exactly why Faiss pivots to those scalar and multi-codebook methods to handle the truly massive data sets. Finally, Section 5, Smart Search, Refining Results. This right here is the absolute crown jewel of Faiss, combining the best of pure speed and exact accuracy.
Let's move to and see how this builds into what's called the index refine process. It's a beautifully simple 2-step trick for achieving fast rough searches and accurate final results. Step 1. You query a fast, heavily compressed index just to grab a rough short list of potential results. Then, step 2, you compute the slower, perfectly exact distances, but only on the vectors in that specific tiny shortlist. You get the speed of an approximation with the pinpoint accuracy of brute force right at the finish line.
Actually, scratch that. Faiss goes even further. Techniques like Polysemous codes mean developers don't even need to hoard memory with 2 completely separate indexes. They literally use 2 ways of interpreting the exact same compressed vectors. It takes a fast, blurry glance at the compressed codes to build the shortlist, and then a slower, sharper stare at those same codes for the final ranking. It optimizes memory incredibly well.
So what is the final result of all these mappings, quantizations, and refinements? 1 trillion. No joke. Faiss' sheer scale and meticulous approach to memory management give it a real-world capability for 1 trillion scale indexing. That's enough to power the massive semantic memory and retrieval systems that major tech platforms absolutely rely on every single day.
So we've seen how Faiss totally stretches the limits of computational geometry and memory. But the core challenge is always going to be there. With finite memory and finite time, how will you balance the speed and accuracy trade-off in your next AI application? I really hope this explainer gave you a solid map to start making those architectural decisions for yourself. Thanks so much for joining me on this deep dive, and keep building.